So welcome everyone to the first after lunch session and the first quantum session of the conference of two. So we are going to be starting with a talk by John Bastanji, which is one half of a soft merged pair of talks, so this will be a short one. And I would like to, if you can kind of leave your questions until the end of the second soft merge talk, then you can ask John and Amit at the same time. Great, so without further ado, John's going to tell us about oracle separations in the quantum setting.
Yeah, thanks, Nick. So I'm going to spend the first part of the talk motivating the problem. So here I've drawn sort of like a baby version of the landscape of classical cryptography. I mean, there's probably lots of primitives that are missing, but we're fortunate that at least at the very bottom in what we call Eurocrypt, we have a lot of equivalences, and we kind of have an understanding that one-way functions are somewhat of a minimal assumption for classical cryptography. Since 2018, though, a bunch of new primitives, what we call like quantum or fully quantum primitives, have kind of jumped onto the scene, and for a long time, it was like not clear what the relationship between these primitives and classical cryptography was. And in the past, I would say like 3 or 4 years, we've kind of gotten a more clear understanding of how things relate. So starting from this awesome paper of William Kretschmer in 2021, we know that many of these quantum primitives, although they're implied by one-way functions, they don't necessarily give us one-way functions, and therefore have the potential to be like more minimal than one-way functions. So given that we now know about things that are potentially more minimal than one-way functions, like these quantum primitives, it's kind of a natural question to ask, like what is the most minimal assumption you need to make for cryptography to exist? In particular, like these guys at the bottom. Among these guys at the bottom, what are the minimal assumptions? Like which of them is the most minimal? In particular, I'll highlight so there's like this kind of category of EFI, quantum bit commitments, and quantum multi-party computation. And then on the side there's like one-way state generators. So this work is going to be focused on understanding which of these two is more minimal. Yeah. So in order to talk about these things, I first need to define them for you. So one-way state generators, they're a family of states that you can efficiently generate and also efficiently verify if you had the key and the state. But no adversary should be able to to go from the state to the key. More formally, a one-way state generator scheme is correct if the verify, given the key and the state corresponding to the key, accepts with overwhelming probability. And also, it's secure if for all efficient adversaries A, you sample. So basically, you pick a random key, you give the adversary copies of the state corresponding to the key, and it can't guess a key k prime that would pass verification with more than negligible probability. Okay, so that's like one of the two primitives that's vying to be the most minimal. The other one are quantum bit commitments. I mean, I'm going to say it as quantum bit commitments, but I'll also give you an alternative characterization of them. So in a quantum bit commitment scheme, there's two parties. One of them knows about a bit B that they want to commit to. They generate some state, rho, that depends on B, and they send one of the registers to their friend. And then now they're entangled, and at a later point in time, they send the other register A along with the bit B to their friend, and then the other party knows what the bit was they wanted to commit to. So in particular, they can uncompute the commitment to get the bit. And for those of you who do classical cryptography, you might be confused why this is a non-interactive bit commitment scheme, but it turns out it's a quirk of quantum computing that you can convert any bit commitment scheme to a non-interactive one for any quantum bit commitment scheme. So this is what we call a canonical quantum bit commitment. Yeah. A bit commitment scheme has a few properties that are important. So the first one's hiding. So we want any adversary who gets either a commitment to 1 or a commitment to 0 to not be able to distinguish them except with negligible probability. There should be absolute values there. Sorry, forgot about that. And also, we want it to be what we call binding. So this means that after sending the commitment off, the first party shouldn't be able to switch their commitment from a 0 to a 1, except with negligible probability. Okay? So another way to characterize these, and I'm mostly doing this for Amit, but another way to characterize these is as a EFI pair. So the state that the state that the first party sends, either in the case when they're committing 0 or 1, these have 3 properties that are important. Number 1 is that they're efficient to generate, particularly like the committer generates them. They're statistically far. This is what the binding property says, if you work it out. And then they're also computationally indistinguishable, so hiding tells you that no efficient party can distinguish them. So EFI pairs are just pairs of states that satisfy these 3 properties. They're efficient, they're far, and also indistinguishable. And it turns out to be equivalent to bit commitments because of this thing I told you, that bit commitments can all be made into non-interactive commitment schemes. Okay. The final thing I need to tell you about to understand the result is this common Haar-random state model. So in the common Haar-random state model, there's a collection of states. I'm not going to define what Haar-random means, but just think of them as like uniformly random vectors on a high-dimensional ball. And every party in the world, let's say, knows about gets sample access to these states. So they can press a button and they can get as many copies of the states as they want. It's known from prior work, one of the papers that will be in this session, and also previous work of Prabhanjan, Ananth, Aditya Gulati, and Yao-Ting Lin, that, for example, commitments exist in the common Haar-random state model. I mean, there's a bunch of other things that exist and don't exist, but for the purpose of this talk, the main important thing from prior work will be that commitments exist in this model. And our main result is that relative to a common Haar-random state, so in the common Haar-random state model, with an additional unitary p-space oracle, we can rule out one-way state generators. So combined with the thing I told you that quantum bit commitments exist in the common Haar-random state model, this is a oracle separation, or like a state oracle separation between commitments and one-way state generators. Yeah. I'll tell you, I mean, I'll get back to the implications later, but for now, I think what I'm going to tell you is like why we can rule out one-way state generators. So in particular, I'm going to tell you about an attack on all one-way state generators. And I see I don't have too much time, so I'll make it quick. So so remember the goal is that we want to come up with an adversary that takes many copies of the state, row k, and learns a key k that does well in the passive verification. And the algorithm is very simple. You just like iterate over all the keys. Let's say the keys are size lambda. So you just randomly sample a key k prime to test. You run the verification lambda many times in parallel. If all of them accept, then you halt and output that you found the right key, and otherwise you uncompute them and like continue. So basically you're just going to guess random keys and try to verify until you hit one that accepts. And if you don't, then you just like, let's say if you don't find one after 2 to the lambda iterations, you output bot and give up. So it turns out it's a nice tool from prior work that if you like make these measurements like actually randomly, then doing this measurement, because you've like amplified it lambda many times, won't damage the state you start with. So basically, even though you might be concerned that when you don't find the right key, you could damage your state. It turns out with high probability, you will still find a key that passes verification with constant probability. And then, in the previous slide, I had written like random in quotations, because if you want to, for example, use like the principle of deferred measurement, that would take more than polynomial space. So what you can do instead is use an unconditional pseudorandom generator, which you can do in p space, also against p space, to like have the whole thing run as a unitary p space algorithm. So yeah. The last thing I'm going to leave you with is potential interpretations for this result. So, just to summarize the whole talk so far, basically, in this common Haar random state model, we showed that one-way state generators don't exist and bit commitments do exist. In particular, bit commitments are equivalent to what inefficiently verifiable one-way state generators say. So one interpretation you might have is that inefficiently verifiable primitives are sort of the minimal thing, and efficient verification allows for adversaries to break them. I'm not a huge fan of this interpretation. The one that I prefer is kind of just because bit commitments are still efficiently verifiable if you have entanglement with the original party. So if you know your friend is going to send you the purification of the state, then it actually is efficiently verifiable. So I think the one that I prefer is kind of entangled versus unentangled. So is it efficiently verifiable with entanglement or without entanglement? So that's my take. So this is kind of the new landscape of quantum cryptography. Yay.
Great. Thank you, John. Let's all thank John. And like I said, we'll leave questions to after I'm into this book.
Okay. Can you hear me? Okay. Okay.
Good. All right. Go ahead.
Okay. Thanks. So now I'll be talking about the second work on this topic, New World in the Depths of Microcrypt. So let's get started. So I wanted to give you a slightly different view of the primitives you already saw. Oh, yeah, OK. So quantum cryptography is often based on average case hard problems, where it's computationally easy to generate a hard instance. And there always exists a solution, but it is computationally hard to find a solution given the instance or many copies of it. And in this framework, we can view one-way state generators, that the quantum analog of one-wayness, as John presented, as a basic form of average case hard search problem, where the task of the adversary is to search for a key given the one-way state or many copies of it. Similarly, we can view EFI pairs, the equivalent formulation of quantum bit commitments as John showed, as a basic form of average case hard decision problem, where the adversary needs to distinguish between two mixed states, O0 and O1. In this talk, I'll also be talking about a special form of EFI pairs, where these mixed states O0 and O1 are actually distributions on computational basis states, or you can just view them as distribution on bit strings, so D0 and D1, and with the similar guarantees. Okay, now that we saw these two different kinds of basic average case hard problems, now let's go back to the picture of quantum cryptographic landscape. So as John mentioned, unlike classical cryptography, one-way function is not a minimal assumption in quantum cryptography. And there exists a whole world of primitives called microcrypt that are weaker than one-way functions. And this world contains one-way state generator and EFI. And most cryptographic tasks that we are aware of imply either one of these two primitives, and hence they are candidates for minimal assumptions. And we also know how to build EFI from one-way state generator from a previous work, but the other way around is not known, which is a very crucial question in understanding the minimal assumptions, as also John mentioned. Secondly, I also would like now to add another basic form of quantum average case hard problem, which is average case hard cloning problem, and in the form of private quantum money, which is a very weak form of quantum money that is implied by most other sophisticated forms, such as public key quantum money. However, private quantum money exists in microcrypt, and it implies EFI, but the other way around is not known. And in conclusion, what we can say is that these three different forms of average case hard problem, we know very little about the relation between them. And hence, to address them, we explore the relation among them in these two red directions. And we show that there exists an impossibility result in each of these two directions. So in particular, what we show is there exists a unitary oracle with respect to which no one-way state generators exist, but there exists a QEFID pair, the special form of EFI. And hence, this shows a separation between one-way state generator and EFI and other associated primitives. Moreover, and this work, as you already saw, is concurrent with two other works. one, as you saw in John's talk, and another one that you're going to see in the next talk. Secondly, we also show that there is no black box, fully black box construction of private quantum money from QEFID. Okay. Now that we have these two results, how does this change the picture? So first of all, our results show that EFI could probably be the weakest minimal assumption, unlike one-wasted generator, because there can exist cryptographic tasks such as commitments even without one-wasted generator. Secondly, we see that microcrypt itself is not a monolith, and there are at least two worlds inside microcrypt. The top world containing one-wasted generator, private quantum money, etc., and the bottom world containing EFI and others. Moreover, the primitives at the top, you can, if you see, they can be associated with an efficient verification for the solutions, either by definition or there's a canonical way to do so, but no such generic method exists for the bottoms for the primitives in the bottom. So as John mentioned, this shows like a demarcation of microcrypt itself into efficiently verifiable and inefficiently verifiable primitives. And therefore, what we can conclude is that efficient verification in quantum cryptography does not come for free, and it comes at a cost of assumptions, unlike classical cryptography. Okay, now let's look into one of the results briefly. So I'll focus on the separation of one-wasted generator from QEFID. So for that, we follow a two-oracle recipe. So the first oracle is a hardness oracle that gives sufficient techniques to construct QEFID. And the second oracle is an inversion oracle, which is strong enough to break any candidate constructions of one-wasted generators. Okay. What is the hardness oracle? So usually, previous works have used the common Haar random state model, but here we use a new oracle that we call the S oracle. And here what happens is that we first sample a uniformly random subset of lambda bit strings, of non-trivial lambda bit strings, so we don't take the 0 to the lambda, of size which is super polynomial, yet asymptotically smaller than the total set. And then what we do is we conceive this unitary US, which toggles between the states all 0 and ket-s, that it maps all 0 to ket-s and ket-s to all 0, where ket-s is just the uniform superposition over all bit strings in S. And for any other state which is orthogonal to these two states, it leaves them unchanged. Equivalently, we can look at this US as a reflection about the state S minus, where S minus is just ket 0 minus ket S by square root 2. This equivalence is similar to how Hadamard gates can be seen as a toggle operation between ket 0 and ket 1, but it is also a reflection about the minus state. Okay. The oracle that we actually use is the control version of this, the controlled US, and we'll be calling it the S oracle from now on. So our hardness oracle is this controlled US. Now let's look into fun facts about this S oracle. So first of all, there exists an efficient algorithm E that can query this oracle only constantly many times and prepare these copies of S minus that you saw earlier. But why are these copies important? Because if we have enough copies of S minus, then essentially you can remove the oracle. What do I mean? I mean that if there exists any algorithm A that queries this oracle, then there exists another algorithm A tilde with similar complexity, such that if A maps row to A row using the oracle, then A tilde takes as input row and some additional copies of S minus, T copies of S minus, and outputs a state which is close to A row and S minus, tensor S minus tensor T. Here T, the number of copies you need for the emulation, is actually a function of the number of queries A makes and the precision error you would want. Okay. So now that we looked at these facts, let's look into the construction. So the QEFID construction is very simple. So the first distribution is just the uniform random distribution. And the second distribution is just uniform random sampling from the set S. And it's not too hard to see that if you have the S oracle, then you can efficiently sample from both D0 and D1. Next, in order to show security, we need to show that sample U from D0 and sample S from D1 is indistinguishable for an adversary that makes polynomially many queries to the oracle. And for that, we can use the emulation guarantee of the S oracle to say, okay, it's enough to show that this indistinguishability holds given polynomially many copies of S minus. And this result can be formulated as the closeness between two ensemble of states, namely S and U in the presence of S minus tensor T, where T is polynomial. And we show this using a trace distance calculation. And since this is a statistical lemma, this holds independent of the computational power of A, and hence it holds under any additional oracle, which is independent of S. Okay. So now we have the hardness oracle. What is the inversion oracle? Well, it's the same as that John and others used in their work, which is the QP space machine oracle, as they called it, the unitary p-space oracle. And here the main idea that we use is to use the gentle search algorithm of Aronson, but after removing the oracle using the emulation guarantees of the S oracle. And with that, I would like to conclude.
Are there any questions for John or Amit?
Yeah, go ahead.
Can you?
Maybe this is a bad question, but why doesn't the quantum p-space oracle also break one-way puzzles?
Because in order to break the quantum puzzle, you need to, like at least in our technique, we need to do the gentle search algorithm using the verification algorithms, which is not efficient for one-way puzzle. So therefore, you cannot just give it as an efficient POVM. And so in order to use the gentle search and have polynomial mini copies, you need the POVMs to be efficient. But if you have a one-way puzzle, the verification is not necessarily efficient.
I might ask more offline.
Sure. Yeah, exactly. It breaks efficiently verifiable one-way puzzle.
Okay, maybe we should take it offline. Are there any other quick questions? Or, okay, great. So let's thank John and Amit again. Yeah, so it's all set up. Sorry? Oh, the clicker. Where did it go? Okay, one second.
Okay, please.
Yes. Okay. Good. So next up we have Boyang Chen from Tsinghua, who is going to tell us about quantum pseudo-randomness.
Okay. Hello, everyone. I'm Boyang Chen. And today I'll talk the work which is the prior work of last talk about how to construct a quantum cryptography, assuming that we have access to a solely random state. Okay. So first, we consider the classical cryptography with common randomness. In the common random string model, a trusted third party can sample random string and distribute it to Alice and Bob. Alice and Bob can interact dependent on the random string S. And this is a very useful model in classical cryptography that can help build cryptography primitives like NISC. Okay. But there isn't unconditional cryptography in the common random string model. So our question is, what is the case in the quantum setting? In the quantum setting, somewhat surprisingly, is that there is unconditional cryptography in the common random state model. In the common random state model, a high random state, polynomial many copies of high random states are distributed to Alice and Bob can interact with each other, and the interaction may depend on the random state psi. And this model is called, as John had told you, it is a common high random state model, and we will abbreviate it as a CHRS model. To introduce what cryptography it can make in this model, I want to first introduce you some basic concepts in quantum cryptography. So the main cryptography primitives I considered in this talk is pseudo-random states, which is introduced by G. Liu Song in 2017. L-copy pseudo-random state family is a state family phi k that it can be efficiently generated given a secret key. And also, L copies of phi k is indistinguishable from L copies of high random state phi. High random state here means that uniform distribution over the states. As a special case, when L equals 1, a 1 PR's family is a state family such that a single copy of phi k is computationally indistinguishable from a totally mixed state. And also, if the secret key is at least as long as the number of qubits, it will be a trivial primitive. So we require, it was somewhat similar to the PRG definition. So we require the one copy pseudo-random state family to be non-trivial, only if the number of qubits is greater than the size of the secret key. And what is the application of pseudo-random states? As John had told you, one of the important applications is bit commitment. In bit commitment, the sender is somewhat a digital version of security vault. The sender can lock a bit in the vault and send it to the receiver. The receiver cannot guess what the bit is, if only given the vault but not the key. This is called the hiding property. Okay. And later, the sender can send the key to the receiver, and receiver can open up a bit, and the sender cannot change the bit in the vault, and this is called the binding property. And by Molimai-Yamakawa 22, Molimai and Horan-Yamakawa 24, 1PRS implies quantum bit commitment. So yeah, if we can make 1 PRS, we can do bit commitment in this setting. So the problem is that, so how do we do pseudo-random states in the CHRS model? It is generally in the same field. It is generally the same with the PRS in the plain model, but that we can generate phi k with access to which depends on the polycopies of psi. And also for any adversary A, the adversary A can also access polycopies of psi and L copies of phi k. Still, it should be indistinguishable. And still, yeah, and 1PRS is still required to be stretching and indistinguishable from mixed states. Okay, so now I can introduce our main results. Our main result is that 1PRS exists unconditionally in the CHRS model. As a corollary, by the previous lemma, quantum bit commitment exists unconditionally in the CHRS model. Okay. So here I'll introduce how to construct PRS in our work. The construction of PRS is just 0.45 n qubits of random poly on a single copy of the common high random state psi. More formally, the family of 1PRS phi k can be defined as x to the a, z to the b, tensor I applying with psi. Here, a and b are first and second half of the key k, and k is a random 0.9 n string. And yeah, there is a diagram in the right down corner that can show the circuit. And clearly, it is efficient given a copy of the psi, and it's stretching because it is a 0.9 n to n 1PRS. So here I'll give a sketch of the security proof. So what does single copy security means? It means that given a single copy of the x to the a, z to the b psi, it is indistinguishable from a fresh high random state phi. Okay, but yeah, this should be trivial if we only give a random state psi, but we allow it to be because x to the a, z to the b psi is acting on psi is still high random. But in the CHRS model, we require that it's still indistinguishable from a fresh high random state phi, even if we have access to polynomial many copies of the state psi. Okay. More formally, it is saying that sigma, which is the which is the expectation over k and psi, the x to the a, z to the b, acting on psi, and t copies of psi, and rho, which is the fresh high random state tensors t copies of psi. They should be indistinguishable from each other for any adversary. And in fact, we show that the trace distance, which you can think of it as a quantum analog of total variance distance of distributions between sigma and rho, is at most t squared to the 1.01 to the n, which should be, and t should be at most polynomially large, so this is exponentially small. And our approach to make that is to approximate sigma and rho with maximally entangled states. Okay, so how to approximate rho? Here is a technical lemma to approximate rho with maximally mixed states. So let the density matrix of t copies of m qubit high random states be the expectation of psi tensor t, or psi average over psi being high random, and also the t copies of random maximally mixed states meaning that the expectation of phi u tensor t, and take expectation over high random integers of u. And here, phi u means that the u tensor I acting on the maximally entangled state between the first half and second half of the qubits. And according to a lemma by Harrow 24, these two states are statically close up to a t squared over 2 to the n over 2 statistical error of each other. This is saying that any adversary, if they have t copies, a polynomial copy or excess of these two family of states, they cannot distinguish which family is it sample from. So now we can show the security of 1PRS without stretching. It means that random poly on 0.5n qubits is statically secure. Okay, this is not stretching, but this is just a toy model that will help showing the security later. Yeah. So for the first step, we need to show the security. We need to switch from psi to psi u, which is the maximally mixed state with with Harrow's lemma. It's saying that with t copies of psi, we can replace all the psi with psi u, and we will suffer from at most t squared over 2 to the n error from each other. And then we notice that for a random maximally mixed state, and a random poly on half of it is equivalent to trace out half of the qubits, and the random maximally entangled state tracing out half of the qubits will be exactly the maximally mixed state, which will be exactly equivalent to a fresh high random state. So if we sample the state psi from random maximally entangled states, the x to the a, z to the b on half of the qubits will be perfectly secure. Okay, meaning that it's a perfectly indistinguishable from high random states, fresh high random. And then we can switch back from psi u to psi, and this will again we use Harrow's lemma again, and this will suffer from at most t squared over 2 to the n over 2 error. Okay, so now we show why 1PRS is stretching without stretching is secure. So how can I then show the security assuming that it's stretching? To reduce the key size, the key idea is that we need to decompose the random high random states according to the first qubit. Psi equals 1 over square root 2, 0 psi 0 plus 1 psi 1. Then, typically, psi 0 and psi 1 are close to two independent n-1 qubit high random states, and they're almost normalized. the key observation here is that if x to the a, z to the b, maps psi0, psi1, psi0 plus minus psi1, psi0 plus minus I psi1 of the states to the maximally mixed state, then it must also map psi to the maximally mixed states, approximately on average. And this, in fact, this holds for, in fact, any unitary family that, as long as it can map all these states to maximum mixed state, and x to the a, z to the b is just an example of this. Due to time limit, I don't have time to go through a whole proof, but instead I want to introduce some implications of our results. Okay, what we, as John and Amit had introduced that, and Kretschmer and KQST, these works show that PRS do not imply one function in a Babcock's way, and PRS is enough for many quantum cryptography, like AQY21, MY21. But we are not super sure about what's the relation between single copy PRS and multi-copy PRS. And the CRS model, it's an idealized model, but it helps answer this question in the plain model. The theorem is that relative to the oracle, one PRS exists, but the multi-copy PRS do not exist. The oracle consists of two parts. The first part is a family of common high random states, psi n being n qubits high random states sampled independently. And the second oracle is a qubit space oracle, also introduced by John and Amit. Okay. And I think I still have some time to introduce the attack of the PRS in the CHRS model. Suppose that for simplicity, I will only introduce attack in the assuming that the phi k is of the form gen k applying with psi. Here, gen k is a unitary, not depending on psi. So consider the projector lambda k, which is I tensor gen k dagger swap I tensor gen k, and so this projector is a very nice projector that can separate the phi k from phi, for phi being fresh hard random states. Phi k tensor psi will passes the test of the projector with probability 1, because that's exactly its definition. And the fresh hard random state, phi tensor psi, then phi and the gen k psi will be with high probability being orthogonal with each other. So this will pass the test with probability around 1/2. Thus, lambda k tensor 10n provides an exponential gap between the PRS and the fresh hard random states. Then we use the quantum OR lemma by Scott Aronson, which is saying that if we have a family of projectors and we want to test whether all of them had a small, if we have a quantum state row, we want to test whether all of them had a very small overlap with the projector, or there is some projectors that have very large overlap. So quantum OR lemma is so we just plug in lambda k tensor 10n to the quantum OR lemma, and it will exactly tell us that whether it's pseudo-random states or hard random. Okay. So to conclude our results, that unlike classical settings, unconditional cryptography exists in the presence of a common hard random state. And the follow-up work, including AGL24, BCN25, BMM plus 25, which is these two are the last talk, and also GZ25. We can show there are more quantum crypto primitives that exist in the CHRS model, and also like the EFID and OM puzzles, and also one-way state generators. Classical communication commitment do not exist. And as Amit had introduced, this oracle can also be lifted to a unitary oracle. And there are many open questions like, there are many quantum crypto primitives, and most of them we don't know what's the relation between each other and if there are separations. And this slide is made according credit with Yao-Ting Lin, and that's all my talk.
Great, thank you. Are there any questions for Boyang? Okay, well, you alluded to there being many open questions, so maybe you could give us one.
Okay.
What is your what is the next open question that you know?
Yeah. It's that there are so many quantum crypto primitives, and but only few of them we have figured out what's their relation. So yeah, so there are still many primitive. We can find, say, equivalence or separations between these primitives. Okay.
Okay. Let's thank Boyang again, and.
Okay.
Good. See this clicker is there. Okay. So our next and final speaker for this session is Aditya Gulati from UCSB, who is going to be telling us about pseudorandomness in the Haar-random Markov model. So take it away.
Okay. So hey everyone, I'm Aditya, and I'll talk about pseudorandomness in the inverseless Haar-random oracle model. This is a joint work with Prabhanjan Anand, John Bostanchi, and Yao Ting Lin. The particular definition of pseudorandomness that I'll consider here is pseudorandom unitaries, which are efficiently implementable circuits that behave like Haar-random unitaries. You can think of Haar-random unitaries as as unitaries sampled at random. So particularly, we need two properties. We need efficient implementation, which means given a key k, there should be some polysize circuit gk, which implements a unitary. That is, it maps n qubit states to n qubit states in a unitary fashion. And we need pseudorandomness. So any adversary given access, any computationally bounded adversary should not be able to distinguish whether it's given access to gk for a random key or u, where u is a Haar-random unitary. So what do we know about PRUs already? Well, they were introduced by JLS in 2018. They gave a few candidate constructions, but no proofs for them. Then we had a bunch of works which gave partial constructions on some restricted inputs. All these restricted inputs were non-adaptive. And then we had these two follow-up works where they were able to solve PRUs for all non-adaptive queries. And finally, we had this very nice work by MH24, which told us how to handle adaptive queries. And this question of adaptive queries had eluded us for a very long time, till MH24 gave this very nice path recording framework that gave us a way to handle adaptive queries with respect to Haar unitaries. Okay, so why should we even care about pseudorandom unitaries? Well, there has been a bunch of works that show how to build cryptography from PRUs and PRSs, but we know how to build cryptography from one-way functions, so why should we care? Well, Krishmer showed that quantum pseudorandomness can possibly exist even if one-way functions don't exist. So this is potentially the most useful minimal primitive we can think of. Okay, so we can. So does that mean we can build cryptography without one-way functions? Well, we have so many constructions of pseudorandomness by now, quantum pseudorandomness by now. So of course we can build cryptography without one-way functions. But no, because none of these constructions work without one-way functions. All of these constructions build pseudorandom unitaries from one-way functions, at least until now. And in this paper, we give a potential way to build PRUs from random circuits. So what am I talking about? Well, AQY hypothesized that random circuits can be PRUs. And this hypothesis came from the following lemma, that BHH16 proved that polydepth random circuits were T designs, as in they mimicked Haar unitaries up to T queries. And there was this very nice result last year which said that low depth random circuits were poly designs as long as each gate acted on a little more than log number of qubits. And for computationally bounded adversaries, poly designs and Haar unitaries are indistinguishable. So aren't we done? We have a nice way to construct PRUs, except that sampling these is inefficient. So it doesn't follow the efficiency property. So maybe there's another way to get around this, which is maybe you can do this inefficient process once, which is you can sample this inefficiently once and make this publicly available, and then think what we can do. And here's where the model comes in. So the model I'll be working with is this quantum Haar random oracle model. This model was introduced by BFV20 and CM21, but they were unable to get any provable results in this model. It has been pretty hard proving any results in this model till now, overall. And what's the model? So there's a bunch of parties, P1 through PT, and there's an adversary, and all of them get access to a Haar unitary and its inverse. So you sample a unitary U, there's all these parties, and they get oracle access to U and U inverse. And this model is very similar to quantum random oracle model, where you sample a random function, and all parties as well as the adversary gets access to this random function. And this random oracle model has been very useful in both classical and quantum cryptography, both for constructions as well as separations. And the hope is that this quantum Haar random oracle model can fulfill a similar role. But again, proving results in this quantum Haar random oracle has been hard. So we work in this easier oracle model, which is the inverseless quantum Haar random oracle model, where all parties and the adversary get access to a Haar unitary, but not its inverse. So you sample this unitary U, and all parties get access to U, as well as the adversary gets access to U. OK, so why study this model? Well, first, of course, proving results in this model gives us a way to make progress towards getting results in quantum Haar random oracle model, and also then potentially from random circuits. Second, it gives a very nice pathway to get results from PRUs. In particular, if you get a result in quantum Haar random oracle model, chances are you can get a similar result in the plane model using PRUs. And I'll show one such result that we have. And finally, this is a very natural oracle to prove separations with respect to. A similar model that we saw before was the common Haar state model. And as we saw in the other 3 talks in this session, it has been used to prove many separations. So potentially, this model proves many separations as well. OK, so what results do we have in this model? First, we show that unbounded query secure PRUs do exist in this model. And the construction makes 2 queries to the Haar random oracle. Second, we show that this is the best you can do. So we show that any construction that makes only 1 query to the Haar random oracle is always insecure. And finally, we also show that PRS and PRFS can be constructed with 1 query, and we give the constructions for these. And we get a plane model implication. This is the result I was talking about, which is that you can shrink PRU keys for free in the plane model. So it says that if you have any PRU construction in the plane model, you can always generically shrink the key length for this PRU to be less than the input length. And this was very interesting because the previously known result was much weaker than this. That showed that only if PRU existed, then they could only shrink the key size for up to 1 query. So the new PRU was with short keys, but it was only 1 query secure. OK, so I'll talk about techniques for a little bit. I'll start by talking about techniques for proving general results in this Haar oracle model, and then move on to PRUs. So in general, a primitive in this IQH-ROM always looks like this. There's a bunch of unitaries, and in between those unitaries, you query the Haar oracle. Some of these unitaries might come from the construction of a primitive. Some of these unitaries might come from the adversary. But at the end of the protocol, the final state looks like this. And once you take expectation over this Haar unitary, you get some state called rho, that I'll call rho A. The problem with this state is that it's very hard to understand. In particular, at least before MS-24, we had no idea how to get any structural information from this. When you take expectation over a hard unitary, the state gets very scrambled, and it's very hard to say anything about this. One thing we do know about this is by Schmidt decomposition, it must have a purification. So there must be some psi A, which has an extra purification register E, such that when you trace out this purification register E, this gives us rho A. The problem with the psi A, though, is that it's not unique, and it's still very hard to find. So it seems like we just pushed the can forward. But this is where the path recording framework comes in from MH24. What they were able to show is that there exists this path recording isometry PR, such that when you replace all the queries to U with queries to PR, you get a state which is very close to the purification of rho A. So in particular, there's this purification register E, and after tracing out this purification register E, you get a state which is close to rho A. Okay, so what does this path recording isometry look like? So it takes as so you can think of it as follows. It takes as in the purification register, it has a database, and in the query register, it takes some query X, and it takes a superposition over almost all values of Y, where it returns these Ys to the in the query register and saves in the database that it mapped X to Y. So formally, it looks like this. It takes as input X and some database R, and it takes a superposition over all Y, returning Y. And in the database, it adds this tuple X comma Y. Note that this database is unordered, so it remembers what queries get mapped to what, but it doesn't remember the order of these queries. And we'll call this database the path. Okay, so now we can start talking about how we use this to analyze PRUs in this inverseless random oracle model. The construction of PRUs we have here is UX to the KU. It looks something like this. It has two queries to the common random unitary U, and it has a query to and it applies a poly X in the middle on a little over log number of qubits, and it's still secure. And so how does the state look now? The state looks like the following. There's a bunch of A1 through AT, which are the adversaries unitaries. And in the middle, it either queries U or it queries the construction, which is UX to the KU. So how does the purification look? Or how does this? How do the two settings look? Well, in the ideal model, you have two unitaries U1 and U2, both sampled from the Haar distribution. In the real case, you have two oracles. One is U, and the other one is UX to the KU, or the construction. Once you purify these, in the ideal case, you get two separate paths. In the real case, you get one combined path where both of these oracles save their information. If you query the first oracle in the ideal case, you add XY to the first path. In the real case, when you query the first oracle, you add XY to the combined path. If you query the second oracle, in the ideal case, you add XY to the second path. But if you query the second oracle in the real case, you add this correlated tuple, where the correlation is defined by the key K. So the tuple looks like XZ, and then Z XOR K, Y. So you add this correlated pair of tuples into the combined path. So the final path looks something like this. Ideal case, you have these two separate paths, and it's nice. You can see which path came from which oracle. In the real case, you have this union of two different kinds of queries. One is these isolated points that you get from querying the first oracle. The other are these pairs of correlated tuples, where the correlation comes from the key. What we are able to show is that for most keys, you are able to identify what are these correlated pairs, and you're somehow able to separate them. So given the key K, you can identify where these correlations are, and at least for most keys, and then you somehow can separate them into a separate purification, a separate path or separate database. So how does this help? Well, ideal case, you can think of the state having this purification, as I mentioned, which is 2 separate paths. In the real case, you have this isolated points as well as the correlated pairs, as well as the key register in the purification, as well as the key in the purification register. And as I mentioned, for most keys, you can separate these into two different paths. So there exists an isometry which maps one to the other, at least for most keys. Now note that this isometry is only acting on the purification part of the real state. And since any isometry being applied on the purification does not change the state, this leads to the ideal state being close to the real state. And that proves that the PRU is secure. Okay, so going over the results and some open problems. So we were able to show that there exists an unbounded secure PRU in the quantum Haar random oracle model, and this construction makes 2 queries to the oracle. We showed that this is the best you can do, and any single query construction is not secure. We showed you can construct PRS and PRFS with one query to the oracle, and we got this plain model implication, which was that you can shrink PRU keys for free. A few open questions and follow-up works. One is that can you construct PRUs in QHROM and not in this IQHROM? Second is, can you get an LOCC lemma for QHROM? Recently, there have been a few LOCC lemmas, and they have been very useful in proving separations in microcrypt with QCCC primitives. So can you get a similar lemma for QHROM? Third is there a way to instantiate this, even heuristically? We generally consider the random oracle model being instantiated with the hash function or something similar. So can we get something here? And lastly, can you instantiate this Krishmer's oracle in QHROM somehow? The Krishmer's oracle is exponentially many Haar unitaries, and it would be interesting to see what results from Krishmer's oracle directly translate to this QHROM. And there's been a few follow-up works. So first, with Prabhanjan, John, and Yauten, we were able to show that PRUs do exist in Haar random oracle model. In fact, strong PRUs also exist in the Haar random oracle model, and this will appear in crypto. And with Prabhanjan and Yauten, we were able to show LOCC lemma for inverseless model, which results in separations of PRU with QCCC key agreements and commitments, and also some partial results about LOCC for QHROM, but not the complete result. It would be interesting to see how we can get a complete result for LOCC. And that's it. Thank you.
Thanks, Aditya. Any questions? Yep.
So just at a glance, looking at this path recording technique that you sketched, it looks very similar to the compressed random oracle technique from QROM. Is there any connection there?
So any connection we have found is a little superficial. We haven't found an exact way to connect both of them. One interesting thing is in compressed oracle, you somehow measure the database at the end. In this path recording, you don't. So it works in sort of any basis, whereas the compressed oracle works only in computational basis.
So how do you avoid problems with everything being uncomputed from the database then?
In this case, you don't have this uncomputation thing, whereas in compressed oracle, you have this. That's another thing which is different about both of them. Here, in fact, you can have multiple x's mapping to different y's, and they'll get stored in the path.
OK, thank you.
Great. So let's thank Aditya and all the speakers from this session.